Our next speaker will join us online, and it is Kohei Hirata who will present to us solving diversity-aware maximum inner product search efficiently and effectively. Let's see if the transmission works. Yeah, floor is yours.
Okay. 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 Hello, everyone. I'm Kohei Hirata from Osaka University, Japan. I would like to introduce solving diversity-aware maximum inner product search efficiently and effectively. In this study, background is matrix factorization, MF. MF is one of the most frequently used techniques in recommender systems. And by recent studies, MF recommendation systems perform better than neural network-based recommendation systems. So this study assumes a recommendation system using MF. MF decompose rating matrix into a user matrix and item matrix. In MF, high inner product between user and item vectors implies high relevance. Then, K-maximum inner product search has been studied extensively. K-MIPS retrieves K item vectors having the highest inner product with a query user vector. A K-MIPS result corresponds to a recommendation list. However, this recommendation list tends to contain similar items that lead to low opportunity of getting new notices. And K-MIPS considers only preference, and diversity is not considered at all. From this background, we address diversity-aware K-MIPS problem. Our study is the first study addressing this problem. Its input is a query vector Q, a set P of item vectors, an output size K, and a diversity degree lambda. Output is a set star that maximizes the objective function Fs. In the objective function, inner product is computed from the vectors generated by matrix factorization. Inner product corresponds to preference, and distances are computed from the vectors generated by item to back. Distance between each vector generated by item to back corresponds to a similarity. Distance is equal to distance, and C is a scaling constant. This definition considers 3 points. First, status contains items having high inner product with Q. Second, the items in a star are dissimilar to each other. In other words, they are diverse. Finally, users can control the degree of diversity through lambda. We did a case study by movie length dataset. Left list does not consider diversity, and it includes only Harry Potter movies. Right one has diversity. It has various kinds of movies with high inner product IP. This problem is NP hard, so we use a greedy algorithm. First, it adds the item having the highest inner product into S. This is done by scanning all items. Second, it computes the score of FPS for each remaining item vectors, then add p star having the largest score into S. This is also done by scanning all items. FPS is derived from objective function, and this is repeated until the size of S becomes K. Time complexity is order nk. Its bottleneck is computing score for each item vector. In each iteration, we want to have a single vector, but the algorithm accesses order n vectors. This is redundant. So we address this efficiency issue. We propose IP greedy. IP greedy returns the same result as that of the greedy algorithm. We achieved identifying a pista without computing its scores. This is based on two techniques. One is early stop. This can avoid scanning all items. The other one is item level skip. This can skip computing score. Next, I introduce our findings. As an assumption, item vectors is sorted by descending order of gamma. Here, gamma is the key of item. This norm of vector obtained by MF, it can be computed offline. Then we have theorem 1 and 2. Theorem 1 filters unseen vectors, so we don't need to compute their scores. This inequality checks whether unseen vectors satisfy the necessary condition for being P star. If this is true, we can early stop the scan, and intermediate P star is P star. Next, theorem 2 skips computing the score for a given item. This check also does not need distance and inner product computations. The overall framework is similar to greedy. IP greedy has several differences. In the first step, we use Cauchy-Schwarz inequality to avoid the wall scan and update sort key. In the second step, we do a partial sort items by using the sort key gamma. Then we compute a pista by employing theorem 1 and 2. And step 3 is update S until the size of S becomes K. In experiments, we measured 3 criteria: time, MMR, and mean dist. Time is running time until S is returned, and MMR is value of the objective function. Larger is better. And a mean dist is the minimum pairwise distance in S. A larger value means higher diversity. Evaluated algorithm are these four algorithms. IP greedy is our algorithm. Greedy is the baseline algorithm. And Pro is the state-of-the-art exact 𝑘-MIPS algorithm. Scan is the state-of-the-art approximate 𝑘-MIPS algorithm. Pro and Scan don't consider diversity. First of all, IP greedy runs faster than greedy. Here and so on. Again, IP greedy returns the same result as that of greedy. That means IP greedy is better than greedy. Let's compare IP greedy with the pure 𝑘-MIPS algorithm. From the MMR and mean dist result, IP greedy clearly provides a higher diversity than the 𝑘-MIPS algorithm. To summarize, we formalize the diversity-aware 𝑘-MIPS problem. We propose IP greedy that returns the same solution as the standard greedy algorithm, and from extensive experiments on real datasets, IP greedy is efficient and guarantees a more diversified result compared with 𝑘-MIPS. Source code is available our GitHub page. Thank you for listening.
So we do have a very burning questions with lots of votes on Slido, which is, why do you use the item embeddings from item to vec instead of directly using the item embeddings that come out of the matrix factorization when calculating distance?
Okay. Vectors are generated by matrix factorization can't represent item relations. So we use item to vec which can represent item relations.
Okay.
Okay.
We have another question that goes in a similar direction, which is why you consider the different item representations for distances and the inner product instead of taking the same vectors. Is that the same argument that you would make for this?
Sorry. Could you say that again?
Why do you consider a different item representation for distances and the inner product instead of taking the same vectors?
Okay. Let me see. Inner product between item and item cannot represent item relations. So we use item to vec to represent item relations in distance, by distance.
Okay, there is a follow-up question that just came in on this. So the distance can be computed in many ways. Why didn't you compare other distance definitions? Are you confident that item to vec distance is the similarity? Should I repeat the question?
Sorry. Sorry, could you say that again?
So how confident are you that item to vec distance is dissimilarity, and why did you not consider something different as a measurement?
I'm
That's okay. Maybe you can answer the question offline. You can read through it and then give an extended answer in the system. Thank you very much to the speaker again.
Thank you.
Now, next up, we have actually